We're going to do a lot today. Do some heavy lifting. We're going to start off talking a little bit about rolling without slipping. So things related, not to gears, but to just rolling. And then we'll get to this principle that undergirds Lagrange's equations, but you could see it as a way to get equations of motion in its own right. It's called D'Alembert's principle of virtual work. And it's related to directions in which you could move. So directions in which constraints aren't keeping you from moving, or you get to satisfy the constraints. So those are called admissible virtual displacements. And we'll talk about forces that are either related to maintaining a constraint, or all other forces would be called active forces. So we've in the past decomposed things into forces that come from a potential energy. We'll do that again too. And forces that do not. Well, now this is another division. Forces that come from constraints and forces that do not, otherwise known as active. But let's just dive on in. Okay. I have a prop too. I'm very excited to bring out. So the first thing is rolling without slipping. So this is, it gets first mentioned in chapter 8 of the main textbook on page 298. But it's a good one to consider. So the idea is we've got it's just based on the geometry. We'll assume an idealized disk or circle that's rolling on the surface, rolling without slipping. Your tires, especially as we get into the Blacksburg winter, will roll with slipping. But we're talking about the idealized case of rolling without slipping. So if we set up a coordinate system, let's say an inertial coordinate system that goes through it's right in line with the middle of this disk. Let's call this the center of mass, G. And we'll measure motion that way as X. So we'll call the motion that this is moving, it's X dot. And this is it's a disk or wheel with a radius R. And we also measure, let's call this contact point down here, P. And imagine we've got some other point. Maybe it's some kind of notch. We're measuring an angle, theta. Well, the way that the angle changes, so there's a relationship between X dot and theta dot. And so if we have relationships between the time rates of change of configuration variables, we called that last time a non-holonomic constraint. So theta dot and X dot. And it's this, X dot equals the radius times theta dot. And here's how you could see it. Think of an infinitesimal displacement. Here's my prop. Check it out. It's a foam disc. It's rolling without slipping. I don't know if the numbers look or the letters look right or not. But think of an arc length. If for an infinitesimal arc length of d theta, then the sorry, that's the angle. An infinitesimal angle that this rolls through, d theta, that corresponds to an arc length on the edge of the disk of dx, and dx equals r times d theta. So as this thing rolls, if it rolls an infinitesimal amount, going back to this drawing, just it's dx, equals r d theta. If you divide both of these by dt, then you get this, right? Divide by dt. So this is in the form of a non-holonomic constraint. If you could put it into the standard non-holonomic form. Well, the linear one that we mentioned last time. And it's also the form of equation 13.5 in the Kasdan and Paley book. So we would have, if we say Q1 is X and Q2 is theta, then this X dot equals R theta dot is in the form of, well, A11 Q1 dot plus A12 Q2 dot equals 0, right? We write it as something equals 0. So that means that our coefficients here, A11, this is just equal to 1, and A12 is equal to negative R. And so this is in the standard form. Another way to think about where this rolling without slipping comes from is that if you were to see this thing roll, if we see any disk roll, the point of contact doesn't move. So the contact point is not moving, which means that the inertial velocity of that contact point P is 0. It's 0 velocity. But as this is rolling, we have a relationship for how a point on a rigid body, what the velocity is compared to the velocity of the center of mass. So since this is a rigid body, since the disk or wheel is a rigid body, we've got this relationship of what the velocity of a point on the rigid body must be. P is also, as a contact point, it's a point on the ground. It's also a point on the rigid body. As a point on the rigid body, this equals the velocity of the center of mass plus the velocity of a body fixed frame. So how the disk is rotating with respect to the inertial frame. Oop, I don't know what happened there. Just died. Let's see, how much did it give me? Let me just redraw what I had. Okay. So velocity of the point P with respect to an inertial origin O is the velocity of the center of mass plus angular velocity cross the location of P with respect to G. So what is that as a vector? Up here in this drawing in the left, so this is R, G, no, R, P, G. It's the location of P with respect to G. Okay, so we have this being true, but the contact point is not moving. And this gives us, because the velocity of the center of mass is related to x dot, the angular velocity is related to theta dot. The location of P with respect to G is going to give us R. So this is going to give us x minus R theta dot equals 0. So that's another way to see it. Okay. Now, even though I've been calling this a non-holonomic constraint, it turns out that the rolling without slipping in 2D is also a holonomic constraint. Because if you look at how far this thing will have traveled, look at this arc length that I've drawn, and I'll highlight it in yellow now. This arc length in yellow would be equal to the distance that this has traveled. So we could say that x is equal to r times theta. So x equals r theta, meaning you could write this as x minus r theta equals 0. So it can be written as a holonomic constraint. And usually the term non-holonomic constraint is for constraints that can only be written in terms of non-holonomic constraints. So that isn't true in 2D for rolling without slipping. It is true in 3D for rolling without slipping. So we'll look at the case of a disk that's rolling on a surface and being upright. If it can tilt, then we got some other complications. But in 3D, let me get a handy dandy figure. This is a rolling vertical disk. It turns out that we now have two scalar equations. So this is for a rolling vertical disk. We've got two scalar non-holonomic constraint equations. So it's x dot minus r cosine phi. I'm using the phi is drawn here. So phi, you could see in this diagram, phi is the angle that the disk is rolling compared to the x-axis instantaneously. This sort of dashed path shows its path along the ground, but instantaneously it's rolling in a that contact point is moving in a direction that's makes an angle phi. So this is x dot minus r. The disk is still radius r. Cosine phi times theta dot equals 0. And you'll notice that for phi equals 0, this is just the same as the 2D case. So there's something similar in the for y dot. Y dot is the constraint in for it's y dot minus r sine phi theta dot equals 0. So you have these two things that cannot be written in a holonomic form. So this is just a note, for phi equals 0, this reduces to the 2D case. And we'll do more things with non-holonomic constraints later. I just wanted to show that now. What if we have a system that has both holonomic and non-holonomic constraints? How many degrees of freedom are they? Well, let's talk about it. So if we have if it's an n particle system, things get different when we talk about rigid bodies. But if we have an n particle system, then the number of degrees of freedom, I'll just write it that way, is we've got 3 times the number of particles because these particles could be in 3 space. So 3n would be everything's free to move. Now subtract off, remember we used capital K for the number of holonomic constraints. So you subtract those off. Remember, those have to be written in scalar form of something relating the variables. And then we also subtract off capital S, the number of non-holonomic constraints. So basically, we've subtracted off all of the constraints. So that's the number of degrees of freedom of the system. This is on page, I think it's 587. But it still must be described by a certain minimal set of generalized coordinates. So a minimal set of n generalized coordinates where n equals 3n minus k. So that means when we have non-holonomic constraints, the number of generalized coordinates is always going to be greater than the number of degrees of freedom. Okay, so when s is greater than or equal to 1, so when you do have some non-holonomic constraints, the system must be described or and simulated in terms of more generalized coordinates than there are degrees of freedom. And that's just how things are. All right, so let's look at an example system. It's totally contrived. This is example 13.4 of the book. It's like a baton. Let me get the picture of it. We take two masses connected by a rigid body, and then it's as if we put skates under the two masses. So here's the picture of it from the book. So point P and point Q, it's like we have a dumbbell. It's just a rigid rod with two masses on the end. So two particle, you could either call it a baton or a dumbbell. It's in the plane, and they are rigidly attached. So they are rigidly connected by a rod length L. And then we add blades or skates underneath both of them, aligned the way you see these lines. So I guess this plane is kind of like supposed to be ice or something. Or we add blades or skates, and then it's just a giant parking lot beneath each particle, aligned as shown. So that means it allows instantaneous velocities only in we've shown a body fixed frame here. There's a B1 and B2 direction, so only in the B2 direction is that allowed. So we've got two kinds of constraints. Capital K equals 1. We've got the non-holonomic constraint, which you can write in terms of location of particle Q with respect to O minus the location of particle P with respect to O. The distance between those, let's just say it's squared, is L squared. Right, those 2 points have to just maintain a distance of L, so that's one way we could write it. And also we have a non-holonomic constraint, which is one of them. The way we could write that is that the center of mass for this system, the inertial center of mass, dotted with the B1 direction is 0. So that's a similar way that we wrote that thing last time. If you're bothered that this isn't equal to 0, then there, it's equal to 0. Okay. So incorporating this holonomic constraint, we've got 3 generalized coordinates, right? Because otherwise, if we had a 2-particle system in the plane, like we talked about last time, if they can both move freely, then we've got 2 degrees of freedom for each. But because of this constraint, well, we don't, and we could pick 3 generalized coordinates. So we can pick n equals, in this case, 4 minus, I guess if you're thinking of, well, both particles are constrained to the plane, then we've got that going on technically. So z1 equals 0 and z2 equals 0. So we actually have 3, but you know, who cares about that? We've got n equals 3 generalized coordinates that can describe the system. Maybe it's the location of the center of mass and then this angle. So we've got Q1, Q2, Q3 equals, we got these 3 coordinates that will describe the system. But then this non-holonomic constraint will give us some constraint on the system. So we would say this has only 2 degrees of freedom. Number of degrees of freedom equals 2, but it must be described by 3 generalized coordinates. So this would be, I'm just over here putting this in that general form of a non-holonomic constraint. So that's just giving you an example of a system where you've got both types of constraints. Now, the thing about the number of degrees of freedom is that it doesn't matter, and maybe this was clear from our discussion last time where we went through all those examples. It doesn't matter what coordinates you use to describe the system. The number of degrees of freedom is an intrinsic property of a system. So that's worth writing here. The number of degrees of freedom is an intrinsic property of a system. So it's independent. This is what I mean. It's independent of the choice of generalized coordinates. So the Q's that you pick. So you could use polar coordinates, you could use Cartesian coordinates. The number of degrees of freedom will not change. There's also some terminology here. If the number of variables, so if the number of generalized coordinates, that means the number of Q's, is equal to the number of degrees of freedom, then we call that it's a minimal set of coordinates, which we said for a system that only has holonomic constraints, it's always possible to theoretically find the minimal set of coordinates. On the other hand, if the number of generalized coordinates, like the example above, the number of Q's is greater than the number of degrees of freedom, then that means it's a redundant set of coordinates. This is just terminology. It doesn't necessarily mean you've done something wrong. If you had only holonomic constraints and you just can't find this theoretical minimum, then you've got a redundant set of coordinates. And you could still write the equations of motion for that, but if you have non-holonomic constraints, you're always going to have a redundant set of coordinates. So that's just setting some terminology. We're not yet using that. So now we're going to get into the meat of what I wanted to talk about today, and that's this thing called D'Alembert's principle. It's sometimes called D'Alembert's principle of virtual work. So there it is, D'Alembert's principle. We'll say what it is. It is almost laughably simple, but it's let's not laugh. It's not funny. All right. So suppose we have a inertial frame and n particles. So we'll formulate this in terms of a multi-particle system. So we got a multi-particle system. It will generalize to rigid bodies, but it's easiest conceptually when you think of particles. So we've got a bunch of them. Here's the jth one. So n particles. Here's mass J. We've got a force acting on J. We've got what's the position, right? We care about that. What's the position of particle J with respect to the origin? Jth particle has a velocity, some inertial velocity of particle J. And just so you have an idea of where we are in K and P, the textbook, this is 13.3.1. If you're also looking at Greenwood, and Greenwood will go into more detail, this is section 2.1. Okay. So we've got a setup like this, and we just start with Newton's second law. So Newton's second law for this system, we'd say F, right? F equals mass times acceleration. So we'll say this equals the mass times the, and we'll write it this way, the time rate of change of the inertial velocity. And D'Alembert's principle, and yeah, I guess because there's n particles, we've got one of these vector equations for each of the n particles. D'Alembert just had the insight that I'll rewrite this as something equals 0. Well, it starts with that. So you rewrite this as, and you're like, well, what's gained by doing that? F minus MA equals 0. And that's, it doesn't seem like a whole bunch has been accomplished. If you've taken enough engineering or math classes, we love writing things equal 0. So there are now n of these equations. And this looks like, it kind of looks like a force balance. You've got the actual forces over here, and then this other thing, let's call it an inertial force, but we'll just put it in quotes because we don't really think of it as a force, but it kind of looks like a force. So now dynamics looks like statics if we treat it carefully. So this Fj is, the actual force, and then actual force plus inertial force equals 0. This isn't like the amazing, but now we're going to decompose the forces into something. So we'll decompose the force acting on a particle. And this is the real insight, I think. You decompose it into, so Fj, we'll put superscript act. This is for active forces. Active forces plus forces due to constraints. So we have active forces, and all that means is that they are not forces related to constraints. So this is a force which maintains a constraint, maintains constraint. What do we mean by that? Let me give you a simple example of a block moving on the surface. Okay, so here's a block moving on the surface. We've got a if the block is moving on the surface, you know, here's a, let me come up with a generic surface. Here's a surface, and here's a mass, right? It's on the surface. What's keeping it from falling to the center of the earth? Well, there's a reaction force of the surface that's maintaining that this is constrained to be on this surface. So all we mean is the usual like normal or reaction force. So for this, a block or mass constrained to a surface, we've got a force of constraint. It's kind of holding it up, right? And then whatever other force, maybe like me pushing that block around. Here's the force of my finger moving this around. This is the active force. Just F act. Make that a little prettier. And now we introduce an idea of a virtual displacement. So we imagine this block, what directions, infinitesimal directions, can it move? So what infinitesimal vector displacement can it make, and yet also maintain that constraint? So for this block, it can only move in, and we'll write delta R, small directions that are parallel to that surface. So this is a delta R is the way that we've drawn it here, it's an admissible. That means it satisfies the constraint. It's an admissible virtual displacement. So this might be an entirely new language, but it's part of the construction of D'Alembert's principle. So admissible means it satisfies a constraint. Sometimes the word permissible is used. So like this virtual displacement, if I'm saying that I am parallel to the surface, then this orange delta R does not satisfy it. So that, no, you can't do that. You also can't, virtually go through the surface. So that's out. Only delta R does that. And you can notice that there's a relationship between these. So the force that maintains a constraint dotted with an admissible virtual displacement is going to be 0. Let's put this in black. So the dot product of those two will be 0. So admissible virtual displacements will always be normal or orthogonal to forces of constraint. All right. So in this case, delta R is must be parallel to the surface. we've drawn the surface as straight, but what if the surface was curved, there'd be a force of constraint that's normal to that surface, and delta R, our admissible virtual displacement, will always be parallel to that surface, even if it curves. So if we have suppose we had a mass on a curved surface, or let's just say a curved wire. So here's some kind of curved wire. Then if the mass was at this point, there'd be some force of constraint that's normal. I don't know if it's pointing that way or pointing the other way. All that matters is it's instantaneously normal to that surface. Normal as in perpendicular. And our virtual displacement would be everything that's kind of tangent to this black curve that I've drawn at that point. So delta R isn't necessarily pointing that way, it could be pointing the other way. So think of delta R just sort of spans the space of the infinitesimal virtual displacements. So this direction would not be an admissible virtual displacement. You can't move in that direction. You can only move locally along the wire. Okay. Now, yeah, I guess this is worth noting. When we have a system of particles, the admissible virtual displacements for each particle will be written as delta Rj. Where I'm using Rj as shorthand for the location of J with respect to some inertial origin. Okay. All right, so this, hopefully it's clear what a virtual displacement is. Are there questions about a virtual displacement? Admissible virtual displacements. Because the next thing will be, we're going to talk about virtual work, which is the work done in going through a virtual displacement. So, okay, all right, so let's go to virtual work. The virtual work, this is what I do every day. No, it's a joke. Virtual work, well, this is virtual, right? So virtual work is the work done by the forces in moving a mass through a virtual displacement. So I like drawing the little block on the surface. It's conceptually simple. So for this case, remember, admissible virtual displacements will be something parallel. The force of constraint is the force that's maintaining the constraint. Usually a normal or reaction force is what we've called it in that old-fashioned Newtonian way of thinking. And then everything else would be considered an active force. So again, our decomposition is the force acting on this is the active force plus the force of constraint. That's the total force. So virtual work is the work done by the forces in virtually moving a particle. So it's just sort of imagined, virtually moving a particle through an admissible virtual displacement. Meaning it must still satisfy the constraints. So what will that be? The virtual work, we write it this way. We like using the delta stuff. So delta W is going to be the total force dotted with the admissible virtual displacement. So this will be, we'll write how we've written the force up here. It's the active force plus the force of constraint. So we've got the active force dotted with delta R plus the force of constraint dotted with delta R. But remember what we said up above about this. I mean, the force of constraint is always going to be perpendicular to the admissible virtual displacement. So this thing, we could call it delta W of the constraint is always equal to 0. So the virtual work done by a constraint is 0. No work is done. The only work that's done is going to be work done by active forces. So that in general, this is going to be non-zero. So the constraints forces do no work. They do no work. The constraints are called workless, not worthless, but workless constraints. And it's worth listing some of these constraints that do no work. In some sense, it means that we're going to be able to ignore them. So what are we going to do with this? I'll tell you what we're going to do. We're going to go up here to Newton's law that we've rewritten in this way. And we're going to take the dot product of this with delta Rj, so the admissible virtual displacements for the particle J. And then only some of the forces will survive that dot product, right? The forces related to constraints will go away, and we'll just be looking at Fj active force dotted with delta Rj. So in some sense, we will be projecting Newton's laws into the instantaneous directions in which movement is possible, and only considering those. So that means we don't even have to worry about what the forces of constraint are. So let me list some workless constraints. You might be wondering, what are all constraints workless? I don't know. But here are some workless constraints. So what the example I've been giving, a mass constrained to a surface, like sliding along the surface. So we might say sliding. I mean, related to that is, so this is like a mass moving on a 2D surface, a mass moving on a wire. Rigidity, that's a big one. So just rigid interconnections between particles. Right, if we think of, there's particle 1, particle 2, and they're rigidly interconnected, you could think of that as being related to some force. Let's call it T, and then negative T. For this system, what's the admissible virtual displacement? If I move this particle a certain direction, well, this particle has to move in that same direction due to rigidity. Rigidity. And so when you work out what is the work done in moving through that virtual displacement, it's going to be 0 because of this negative here, right? Equal and opposite due to the rigid interconnections. So rigidity does no work. The ever popular rope pulley system. So here's a little sketch of it. We've got particle. This is our pulley. Here's our rope going around the pulley. And same kind of situation. If there's, there's tension. Well, over here, there's going to be tension is equal, but now the displacements, if this displaces up a certain small amount, well, this has to displace down a certain small amount. So this is now negative delta R1. So if you add up what's the virtual work done because of now this minus sign, the virtual work will be 0. And then the rolling without slipping. So the situation that we started out with, there's some kind of disk and it's rolling, moving that way. This one's more complicated because there are torques that cancel out. So let's just ignore that detail for now. Just remember, okay, these are kind of 5 biggies of common constraints that do no work, all right? And now we're going to use this to take those dot products and get equations of motion only along directions where which satisfy the constraints. So this is what we're going to do. We're going to write the admissible virtual displacements. Well, right, they're displacement vectors. And we eventually want to get to these Qs, these generalized coordinates. How are we going to do that? I don't know. We're going to write the admissible virtual displacement vectors in terms of generalized coordinates. Okay, so that means this delta R for particle J, the admissible virtual displacement, and remember Rj, the location of particle J, can be written in terms of our collection of little n generalized coordinates. So Q1 through Qn. And this J goes from 1 through capital N, the number of particles. Okay. So delta, we're going to write delta Q1 through delta Qn as these are the admissible virtual displacements of the Qs, so of the generalized coordinates. Delta Rj, the admissible virtual displacement vector of particle J, is equal to sum of I goes from 1 to n, the number of generalized coordinates. We're using the chain rule, right? So partial Rj, partial Qi times Q delta Qi. So we just used the chain rule. And I guess if you want to know that we used the chain rule, there it is. So now back to the D'Alembert's principle. D'Alembert. It's fun to say. Must be French. All right, so now we take, right, this Fj minus Mj inertial derivative of, we'll write the inertial velocity of particle J that way. We're just getting rid of this like slash origin stuff because we don't care. All right, and remember Fj, that's like the third time I've written it. Fj can be written as Fj of the active forces, and then Fj of constraint forces. All right, so we take this equation for particle J, and we will, it's kind of not good math, but I'm going to take the dot product of that equation with the admissible virtual displacement vectors of particle J. Okay, that's all we're doing. Dot product, which is the same as, projection, if you want to be really fancy. Dot product of basically Newton's second law with delta Rj, the admissible virtual displacement directions. All right, so on the right-hand side of this, something dotted with 0, you get 0. So yippee. And then on the left-hand side, let's just write this out. Fj active plus Fj constraint minus Mj inertial derivative of the inertial velocity dotted with delta Rj. Okay. Then we'll group these. Active minus inertial derivative of the jth, the velocity of the jth particle, dotted with delta Rj. So we've got that, plus Fj constraint, dotted with delta Rj, and this equals 0. So we've got this. This is true for each particle J. Now we will, so we've got n of these equations, all right? We're just going to sum them up. Well, let's sum them up. So the sum over all the particles, we just add up all of these equations, and we have that. All right, let's, that does not need to have parentheses around it. Let's write this as, right, all of these constraints are workless constraints. So this delta W related to the constraints, it's 0 because these are workless. But then what about this? So this is a sum of dot products, and you'll notice it equals 0. So this also just equals 0 after we sum over all of our particles. And this is the D'Alembert's principle of virtual work. And it could be used to get equations of motion. It's as if we have just projected out, projected only into directions in which motion is possible. So let's try this for the pendulum to get used to this. All right. Let's try it on the pendulum. So this is an example where we're going to apply this because this is pretty theoretical. Here is our pivot point. We'll call this pivot point O. Here's our, and we only have one mass. There it is. Here's the massless rigid rod. So we've got some rigidity, right? A workless constraint. At this point, instantaneously, the only admissible directions, vector directions, would be kind of along the path. Let's call this direction EZ, if you want. Maybe we'll call this direction E theta, right? If we were to use the usual way of writing the pendulum, as it's the angular the angular displacement that it makes from the vertical. So there's for the pendulum, there's a rigidity constraint. Which we would write, if we're using polar coordinates, r minus L equals 0. So this is in, right, polar coordinates, r theta. Because it's rigidity, it does no work. So it's a workless constraint. So that means we don't have to worry at all about the forces related to that, right? Usually we've had to take that into account. Oh, what's the force of constraint? But now we don't care. We're just not going to care. So this system is if you were asked, okay, this is the planar pendulum. What is how many degrees of freedom is this? It's just 1 degree of freedom. And so theoretically, we should be able to find what that 1 degree of freedom is in terms of a generalized coordinate. It's theta. That's it. The system is 1 degree of freedom, right? Free to move in theta. So Q1 equals theta is our only generalized coordinate. And because things are free to move, right? Delta Q1, delta theta is arbitrary. So why are you saying that? When we have more than one generalized coordinate, there could be some relationship between these delta Qs. But in this case, because we just have, that's the 1 degree of freedom, delta theta is arbitrary. It's not constrained. It's just some small infinitesimal change in theta. And what else is true? The location of the particle is dependent on theta, right? So this is of the form, like we wrote above, location of the one particle is dependent on just the one generalized coordinate. And we could get at what that is. So delta R is equal to R delta theta in the E theta direction. And here, because R minus L equals 0, we can, instead of R, we could just write the length of the pendulum. That's L. So this is L delta theta in the E theta direction. We've written the inertial derivative of the inertial velocity a whole bunch of times in terms of polar coordinates. So I'm just going to write out what it is. All right. So this is L theta double dot. I'm getting all of the bits and pieces needed to put into here for D'Alembert's principle. Okay. This is in the E theta direction minus L theta dot squared in the ER direction. What is the active force? We've got this force due to constraints, but we also have an active force due to gravity. because that's the only other force around. The active force is the force due to gravity, negative mg, the EZ direction. So yeah, this mass has mass m. Okay. So the active force is gravity. And we have everything we need for D'Alembert's principle. Okay. Let's just remind ourselves, maybe I'll keep that here. So D'Alembert's principle for this just one particle system would be the active force minus m, and it's mass times acceleration. I'll just remind myself over here, this is just the inertial acceleration. Mass times the acceleration dotted with delta r equals 0, the admissible virtual displacement vectors. Okay, now we'll plug in everything we have for this and see what we get. All right, I'll put it over here. For gravity, we've got negative mg, easy, minus, now we've got ml theta double dot e theta minus ml, now this is a plus ml theta dot squared er, and this is all dotted with delta r, which is just L delta theta E theta. L delta theta E theta. And this equals 0. Now, we could just divide this thing by L, so the L doesn't really matter. Delta theta is arbitrary, so we could divide by delta theta. And then all we're really doing is looking at each of these vectors, taking their dot product with E theta. Okay, so what are we left with? Minus mg Ez dotted with E theta. That's not always going to be 0. And then minus ml theta double dot E theta dot E theta. Oh, that's going to be 1. Plus ml theta dot squared er dot E theta. Well, those two are orthogonal. So this is 0. This is 1. Ez with E theta, you could figure out what that is. You know, it's going to be sine theta. So what we're left with is minus mg sine theta minus ml theta double dot equals 0. Or written as in the form of a second order ODE, theta double dot equals something. What is that something? Theta double dot equals negative G over L sine theta. So this is maybe the third or fourth way that we've now derived this same equation. And that's, you know, the noteworthy thing. What do you know? It gives us the right answer. Same as other approaches. What was the advantage? We didn't have to care about the force of tension in the rod. In some sense, we just projected it out. And, you know, at some points you could see what things are what's gonna shake down here. Like you go, oh, well, I already know E theta with ER 0, so I wouldn't even have to bother to write it out. And I know that with this, it's gonna be 1. So that means the only kind of dot product of vectors that might give me some trouble is E theta dotted with EZ. I'd have to just sort of figure out from the trigonometry what that is. So that is D'Alembert's principle, okay? And some people just sort of stop there, and you can use D'Alembert's principle to get equations of motion for a system without going into Lagrange's equations. And it works out. It works out. Okay. So let's see. Let me show you what you get for a multi-particle system. All right. And this will set up what D'Alembert's principle is for a multi-particle system. For a multi-particle system, you would have Rj as a function of some chosen set of generalized coordinates. And there's a significant, there are these things called projection vectors or velocity coefficients, but we're going to write, you probably saw this in one of the formulas earlier, partial Rj, partial Qi is a vector. We're going to give it a name, which is gamma, and then with superscripts j for the particle and I for the generalized coordinates. Now, it turns out, this would lead to a inertial velocity for particle j, which is a function of the, could be a function of the q's, but it'll also be a function of the q dots. And here's an interesting thing, which is that if you took this derivative here, this partial derivative, it's going to be the same as if you took the partial derivative of the inertial velocity of particle j with the generalized velocity qj dot. Okay, so you could write it either way. It should give you the same thing, but these gamma vectors with these two indices end up becoming important.
Does one of the indices in the fraction have to be an I instead of a J?
Yeah, thanks for noticing that. This should be I. Yeah, good point. In fact, I'll even color these. The first index is the particle. Right, this is for the particle. This is the particle label. And the second one is the generalized coordinate label. So yes, j goes from 1 to n, and then I also goes from 1 to, but it's now little n. It's for the particles. Here's the generalized coordinates. These things, these gamma ji, are called projection vectors by some, or velocity coefficients. If you do the velocity one, and it should give you the same thing. And they play an important role in D'Alembert's principle and Lagrangian mechanics. So often it's like once you've written out what your particles are as a function of the q's, you would write out what these projection vectors are first. All right. And then there's the relationship between how the virtual displacement vector can be written in terms of virtual displacements of the q's, delta r j equals sum from 1 to little n partial rj partial qi times delta qi, but this is also just the sum 1 to n of this, the projection vector with index j I delta q I. So if we now look at the D'Alembert's principle for a multi-particle system, we've got F, and I'm just going to put superscript A instead of ACT. So now FA means the active force, which just means the forces that aren't related to constraints. So active force minus mj inertial derivative of the Vj. If we dot that with the admissible virtual displacement vectors of particle j, that equals 0. And then we could also, right, the D'Alembert's principle had to do with you sum over the index j from 1 to capital N, the number of particles. And then we just recall what we have here for delta rj and plug it in. So we have this sum, j goes from 1 to n, fja minus mj, inertial derivative of vj, dotted with another sum from I, goes from 1 to little n, projection vectors, delta qi. And now we can switch the order of the summation. And so pull out the sum for I, 1 through little n, sum j, 1 to capital N, the active force minus m times inertial derivative of the velocity, dotted with gamma ji delta qi equals 0. So this would be one way to write D'Alembert's principle. And then there's two cases to consider. And we'll just have to get to the two cases next time. That would be, one case is where you have a minimal set of generalized coordinates. Remember what that means? That means that n equals the degrees of freedom. The other case is if you have a redundant set. So if you have a minimal set, then all these delta qi's are arbitrary, and that leads to a big simplification. If you have a redundant set, so that means that there's a relationship between all these delta qi's. So if n is greater than the number of degrees of freedom, there's the delta qi's are related. So there's formulas that relate them, and you'd have to figure it out. But we'll continue with that next week.